If we take a look at an ideal voltage amplifier, let's say this triangle symbol here, it would simply take whatever the input is, multiply it by a gain, A, and provide an output equal to A times V in. So looking at this expression over here, the gain, A, is equal to V out divided by V in. This is the definition of gain, whether it be a voltage gain or a current gain or a power gain. And in our case, we're going to just concentrate for a moment on voltage gain. Now, it seems a little bit peculiar to talk about transistors as a voltage gain amplifier because they're actually a current amplifier. But we can remember that we can always convert currents to voltages by means of passing them through a resistor. So now, what would be the characteristics of this type of amplifier, an ideal amplifier? If we were to take a look at the input of any amplifier, it would generally have some kind of an impedance. Now we're going to use Z as the symbol for impedance because we're talking about AC signals. And the output, of course, can be simulated by means of a voltage source and with a Thevenized output impedance, Z out. And at first glance, you might think that this does not look like that amplifier, but in fact, it does. We can very easily, for example, make this ground, and we make this ground, and we suddenly see that we have an input, we have an output, we have a V in here, and we have some sort of V out here. And the gain of this amplifier over here, this source over here, is simply A times V in. So for the ideal amplifier, for an ideal amplifier, it should have no loading on the circuit ahead of it. So adding this amplifier circuit should have no effect on the previous circuit. And for that to be true, Z in, the impedance looking into this thing here, should equal infinity. It should draw no current at all. And for this circuit to have no loading effect on the circuit after it, or another way of saying it is adding something on here should not cause this to change, we'd have to have the characteristic where the output impedance is equal to 0 ohms. Now, in a real amplifier, of course, this is not the case. So let's redraw this now as a real amplifier. And we'll just put real in sort of semi-quotation here, because a real amplifier has many, many more components than these, but we'll just keep it really, really simple. So again, we're going to have some sort of input impedance, Z in, and we're going to have some kind of a gain times V in. This is V in. And we're going to have some kind of Z out. And now we're going to attach this to a circuit, a real circuit. So we'll simply put in a signal in the input. We'll call it just simply Vs for a voltage signal or voltage source. And it will have an input impedance of a Z, call it S, for source. And we're going to attach over here a load. And we wonder, how does this influence the gain of the circuit once we start including things like an input impedance and an output impedance? Well, we notice now that there's a change in V in. Notice this. There is a change in V in. And the change is that it's reduced, i.e. it is reduced. You see, if we put in a source over here with Vs in it, then V in would equal Vs. But here we have a voltage divider. So V in is now equal to the voltage divider rule, Vs, the source, times Zin over Zin plus Zs. So the input is going to be smaller than what we expected. And notice what happens in the output as well. We'll call this the Vout. Because there's an impedance in here, we're going to lose something in the output because of this voltage divider action. So notice this. There is also a change in Vout, i.e. it is reduced. And we can calculate that handily. Vout is equal to the signal coming in, A Vin, times, now the voltage divider, Z load, divided by Z out plus Z load. Now, because the input has been reduced and the output has been reduced, notice what else has happened. The overall circuit gain is lower than the ideal amp. The overall circuit gain is lower. So what does that mean for us? It means that in transistor circuit analysis, in order to be able to accurately determine what the AC signal gain is, we're going to have to include in our analysis the internal impedance of the transistor. And this, remember, this input impedance for a transistor is basically a function of emitter current. Remember, it is beta times Re prime plus Re, and maybe plus biasing components as well. And likewise, this output impedance will be dependent upon the nature of the transistor and the circuit, the biasing circuit. So we're going to improve our circuit analysis of transistors by taking a look at the biasing network that supports the transistor and puts it into its operating region, because it has a profound effect on the overall circuit gain.